Okay, yeah, so I'll just start now. So uh yeah, Chiao told me that like he wanted me to teach this topic because I don't know why. But okay, so like a quick warning, right, is that today's topics today's topics right are like kind of hard and more advanced. And if you don't understand, like please ask questions if you are confused at any time. So what I'm going to cover today is like mainly two things. The first one is heavy light decomposition, which is more commonly known as HLD. And the second one is central decomposition. So both of these are like techniques that you use on the tree. Yes. And this was first taught in that course in 2019. And yeah, it's quite useful. And in back in 2019, it was not in IOI syllabus, but now it is back in IOI syllabus, so it can be tested. Oh yes, and similar to Chen Hao, I'll be like hiding problems that I'll be going through next week so that y'all can like focus on them more. Okay, so why do we need HLD? So if you consider the following problem, right? If we have a tree and we have two types of queries. One is an update to change the value of HI to V, and the second query is to find the maximum age value of some path, right? Well, we can't if you only have a query if we only have the query and there's no update, we can just use LCA. I think that question is like oranges too. Yeah, we can just use LCA to find the maximum age value. But in this case, if we have updates, LCA will not work. Because when you want to update, right, if you consider a tree, then you have to update like all of its children values. So yeah, that will be like O of n. And also HLD, interestingly, it often works as an unintended solution. So yeah, it's quite applicable to quite a lot of tree questions, if you can think of it. So yeah, I'm going to just go through the background slides because I was too lazy to make my own. Okay, so what is HLD? So when we're doing a pre-order on the tree, we can basically have yeah, so this is like a subtree to range, right? So when we're pre-ordered on the tree, sometimes we have a family or a segment tree on this subtree. Then we can that gives us like some, let's say you want to like add values to a node and you want to query like the sum of values on all nodes within the subtree, you can use this. But what if we want like the sum of all values on the path? Then we cannot just use this because this gives a subtree. We want the path. So what HRT serves to do is it divides the graph into a lot of lines, and each one we can apply family or symmetry to it. Yes. So this is how HRT works. So basically, a tree can be divided into many paths. So if we do this randomly, right, we could end up with too many paths. But yeah, HRT does it like in some greedy order. So basically, you assign, you have like heavy and light children, and the child that is the heaviest will be like prioritized first. So yeah, so what this means is that like if you look at this, right, in this tree, here, okay, in this tree, right, two has the most. When you start with DFS at 1, 2 has the most. 2 is like the largest, so we prioritize to DFS into it first. So when you look at the children of 2, 4 is like the largest subtree, so we'll DFS into it, and so on. So this path this red buff is called a heavy buff. Yeah. And after you DFS into all your heavy children, you you'll be left with your like all your light children. Then you'll DFS into your light children after that. So yeah, you this for the 4 to 11 age is called like a light age. So it's basically like your children, everyone else who is not your heavy children. Then after you DFS into 2, right, you also have a DFS into 5 up, which is a light child of 1. And 5 will have its own heavy children too, which in this case it will be 6. Yeah, so the heavy child 5 will be 6, and you DFS into 6 first before 7. Uh, yeah. No, HLD is not excluded by open discussion. Look at this symbol. It's a thick and a dark file. That means it's included. Yeah. They changed it quite recently. Oh, okay. Yeah, back to our lecture. So wait, does everyone follow so far? Okay, wait, this is a summary. Yeah, so far we have covered like the first part. So yeah, so what we do is we have a tree and we just break them down into like some lines are. Then how we define the lines is the a heavy child will be the child with the largest subtree size. So in this case, it will be, and everyone else is like a light child. Then heavy age is between a parent and his heavy child, and a heavy buff is just like a buff of heavy ages. Yes. So after we do this, we can just build our data structure on each of the heavy buffs. Yeah. In total, like the symmetry of n nodes are because like in total there are only n nodes in our entire tree. So I mean, yeah. Actually, then okay, that actually n minus 1 ages. We are building it on the count of the ages. And that depends on how you code it. And normally we will code it just in one big segment tree, and we will like have like an index for each path. So it will be like a global running counter. So let's say we start from 1, right? Then the 1 to 2, this age will be age 1, the 2 to 4 will be age 2, 4 to 8 will be age 3, and 8 to 9 will be age 4, and so on. Then yeah, then 1 to 3 4 to 11 will be age 5, and 2 to 3 will be age 6. And so wait, let me explain that in more detail. Choose the color. yeah, so it's kind of like pre-order labeling, but we'll be visiting our our heavy trials first up. So we'll label this age like H1, then this will be H2, this will be H3, this will be H4, then this will be H5, this will be H6, this will be H7, then. So what I notice about this, right, is that all of the heavy bars will have like consecutive indexes, and this will allow our segment tree to be built with only one segment tree instead of having like a lot of segment trees. Yeah, so yeah, this is normally how people normally code it. Then okay, so what does this work like? It was because the number of the number of heavy bars between any pair of nodes is at most O of log n. So why is that true? Is because the number of heavy bars between any node and the origin is O of log n. And why is it true? The proof is here. So it's, it's basically because like every time you quote unquote merge it with like another with all your other fellow children of like a node, right? Your subtree size basically at least doubles. And since we have like at most, and since we have like n nodes in the goal, we will need to traverse up top n light edges. And since we have at most down light edges, it also means that we have at most log n heavy edges. So at most log n total light edges plus heavy buffs. So because of this, every pair of nodes, right, we have at most we have just like log of n heavy buffs or light edges between them. And since each segment tree is O of log n, each segment tree operation is O of log n, our each query time complexity will be O of log square of n, or log of log n square. Yeah. So how do we code this? I mean, I've pasted a sample code here for discussion. But the key idea in this game, for every node, we'll find for every node, we have to find its head. So the head of this node is usually like uh the least depth element in the baby path that is located in. So for example, here the head of 9 will be 1. So it's the head of 8, and the head of 4, and the head of 2. For the head of 10 and the head of 6, and the head of 5 are all 5. So the head of 1, 2, 4, 8, 9 is 1. 5, 6, that is 5. For the head of 3 at 3, 7, and 11 is just itself up. Yeah, it is like a path with no edges. Head of 3 is 3, head of 7. So this will basically allow us to like traverse up the heavy bars quickly, because from 9 we can just straight up jump to, we can just traverse, we want to traverse all the way up, we can just jump all the way to 1 without having to like go through one by one of its parent. Yeah, so for every node, you just repeatedly update everything. So let's say you are trying to like find the maximum between 9 and 6, then you can just jump from 9 to 1 and do one segmentary query for like the maximum value, the maximum value of the agents there. And yeah, and after that, right, since 1 is above 6, you look at 6 and you can jump to 5. And if it's at the head, right, then it will like go up one more, so to go to 1. You can query that also. So that will be like the light edge queries. Okay, yes. Yeah, so these like kind of like the stuff that you store in your, that you have to store. You have to store the index of the node in your, this is basically like the pre-order position. And the head is the top of the heavy path. And what's sub? Oh, sub is just the subtree size, I think. Yeah. The subtree size you need to come to find out which of your children is your heavy child. And yeah, here's like the code. First you do a DFS to find each node's heavy child. So basically it's like you're just finding the size of every single subtree. And for each node, you look through all your children and you just find which one has the largest subtree. Then your second DFS would be the HLD decomposition DFS. So you basically just go to the heavy child first. So this will ensure that your indexes will be consecutive for each heavy path. Then after you decompose finish, then you look through all your other light children. You DFS into them. Yeah, you can try using HLD on origins too, but I mean this question can be solved using LCA, so because there are no updates. Yeah, so to summarize, what we do is that we'll break down a tree. HLD just breaks down a tree into many heavy paths and light edges. So how this is defined is a heavy child of a node is just a child with the larger subtree size. A heavy edge connects the node to its heavy child, and the heavy path is just heavy edges joined together. And every time it defines light, so the opposite. Yeah. Then for each heavy path, you just build a symmetry on it. And you can show that the path between any pair of nodes contains O of log n heavy paths and light edges. And because of this, right, we can just do symmetry queries and updates on all the heavy paths. And every query will run in dots, not in square time. Okay, so this is our example problem. It's basically the problem here. Yeah. So the bridge statement, I mean, the statement is quite short. So yeah, usually you have to support like class of queries. One is change the cost of HI to T, and the second is query the max edge cost on the path. So the question whenever you want to do HLD is you need to ask yourself is, if the tree was in line, right, is this solvable? So in this case, if the tree is aligned, I think it's quite easy to solve. Just a basic symmetry. be like point update and range query. So only when the tree is aligned and you solved it, can you apply HLD to it, because you need to implement the data structures on all the files. So you can just combine the line solution with HLD to get a full tree solution. Yes. Okay, so our learning points is that HLD basically breaks down the tree into many lines. So when a problem has updates in creation files, we can use HLD. But you still have to solve it like if it's a line